Have you ever pondered about the environmental impact of concrete production? Concrete, the most widely used man-made material on the planet, is not just the backbone of our cities and infrastructures, but also a significant contributor to global carbon emissions. Astonishingly, the production of concrete accounts for about 8% of the world's CO2 emissions. That's more than twice the carbon footprint of the entire aviation industry. This sobering fact underscores the urgent need for innovative and sustainable solutions in the concrete industry. Reducing the carbon footprint of concrete is not just about ticking a box for environmental responsibility, it's about creating a sustainable future for our planet, for us, and for generations to come. So, with the stakes so high, how can we shift the balance? How can we transform this ubiquitous building material into a part of the solution, rather than a part of the problem? So what can we do to curb these emissions? Let's delve into some fascinating methods of carbon capture. First up, let's explore direct CO2 capture. Picture this: massive industrial facilities belching out plumes of carbon dioxide, a key contributor to global warming. Now imagine if we could capture that CO2 directly from the source before it ever reaches our atmosphere. That's exactly what direct CO2 capture aims to do. By employing advanced chemical techniques, this process seizes carbon emissions right from the exhaust stream of industrial operations. It's like a giant vacuum cleaner for greenhouse gases. The beauty of this method is that it can significantly reduce the carbon footprint of various industries, including concrete production. But it's not all roses. There are challenges to overcome, such as the high energy requirements and the need for safe CO2 storage. Despite these hurdles, direct CO2 capture is making headway in our fight against climate change. It's a promising start, but as we'll find out, there's more to uncover. Next in line is carbonation of concrete. Now this is a fascinating process where carbon dioxide, a notorious greenhouse gas, is chemically reacted with calcium compounds in hardened concrete to form calcite. This not only locks away the carbon dioxide, reducing emissions, but it can also enhance the mechanical properties of the concrete itself. Yes, you heard that right. We're essentially turning a harmful byproduct into a beneficial ingredient. However, like any innovation, this method also comes with its challenges. For instance, the rate of carbonation is quite slow, and the depth of carbonation in the concrete is often limited. Also, the overall carbonation process requires a significant amount of energy, which could potentially offset the environmental benefits. But remember, these are hurdles to overcome, not deal breakers. With advancements in technology and research, we might soon be able to optimize this process for maximum benefit. Incredible, isn't it? But hold on, we've got more exciting methods to explore. Now, let's shift our focus to alkaline activation and bio-based carbonation. Alkaline activation and bio-based carbonation are two intriguing methods of reducing the carbon footprint of concrete. They may sound complex, but their core concepts are fairly straightforward and fascinating. Let's begin with alkaline activation. This process circumvents the need for traditional cement, which, as we know, is a significant contributor to carbon dioxide emissions. Instead, we use alkaline activators to stimulate a reaction in certain materials such as fly ash or blast furnace slag. The result? A binder that can replace cement in concrete production. Now that's a win for Mother Nature. However, like any good story, there's a twist. The challenge lies in the production of these alkaline activators, which can also generate carbon emissions. But fear not. Researchers are tirelessly working on finding solutions to minimize these emissions, turning this into a truly eco-friendly option. Next up, we have bio-based carbonation. This process involves using microorganisms to naturally capture and store carbon dioxide. Imagine that tiny organisms working around the clock to trap harmful greenhouse gases. It's nature's own carbon capture technology. The bio-cement produced from this process can be used as a replacement for conventional cement, reducing the carbon footprint of concrete. However, scaling this process up to an industrial level presents its own set of challenges. It requires careful management of the microorganisms and the conditions they need to thrive. Despite these challenges, the benefits are substantial. Not only do these methods reduce carbon emissions, but they also have the potential to enhance the mechanical properties of concrete. Yes, we're talking about stronger, more durable concrete. In conclusion, alkaline activation and bio-based carbonation offer promising alternatives to traditional concrete production methods. They represent a step towards a more sustainable future, where we build our world without compromising the health of our planet. While these methods are quite intriguing, there's one more method that's worth exploring. Finally, let's delve into the world of nanoadditives and life cycle assessment, LCA. The story of concrete doesn't end with its creation. The journey continues as we explore the marvels of nanotechnology and the role it plays in enhancing the mechanical properties of concrete and reducing its carbon footprint. Nanoadditives, minute particles 1/1,000,000th of a meter in size, are added to the mix of concrete to improve its strength, durability, and permeability. This not only helps extend the lifespan of concrete structures, but also lessens the demand for new materials, resulting in a decrease in carbon emissions. Imagine a world where concrete structures last centuries, not decades. That's the power of nanoadditives. But the story doesn't end there. While nanoadditives are revolutionizing the world of concrete, it's important to consider the broader picture. This is where life cycle assessment, or LCA, comes into play. Life cycle assessment is a tool used to evaluate the environmental impact of a product from its cradle to its grave. It takes into account all stages of a product's life, from raw material extraction through production, use, and disposal. For concrete, this means considering the impact of mining raw materials, manufacturing processes, transportation, and end-of-life disposal or recycling. However, as promising as these methods sound, they aren't without challenges. The production of nanoadditives is still a costly and energy-intensive process, and life cycle assessment requires comprehensive data and careful interpretation. But the benefits? They're potentially enormous. By using nanoadditives, we can create stronger, more durable concrete, reducing the need for frequent replacements and thereby lowering emissions. And with life cycle assessment, we can identify hotspots of environmental impact, enabling us to focus our efforts on making the production process as sustainable as possible. With these methods, we can surely make a difference in the carbon footprint of concrete production. So what have we learned today? We've explored the intriguing world of concrete production and its carbon footprint. We've delved into the practicality of direct CO2 capture, where carbon dioxide emissions from industrial sources are captured and stored, reducing their impact on our environment. We've learned about the carbonation of concrete, a method that incorporates captured carbon dioxide into the very fabric of our buildings, reducing emissions while potentially enhancing the mechanical properties of the concrete itself. We've also discovered the potential of alkaline activation and bio-based carbonation, innovative approaches that could revolutionize the way we think about concrete production. Finally, we ventured into the realm of nanoadditives and life cycle assessment, exploring how these small-scale changes can have large-scale effects on our carbon footprint. Together, we can build a greener and more sustainable world. Thank you for joining us on this journey. Stay tuned for more enlightening discussions.